a perfect number is an integer that's the sum of its proper divisors. Now, it turns out there's a form that you can develop in a number theory course that corresponds to primes. Let's talk about the prime number 2. All right. Now, if you put 2 in here for p, you would get 2 times 3. All right. So that would imply 6 is the first perfect number. Now, if you doubt that, just notice that 6, the proper divisors of 6 are 1, 2, and 3. And if you sum up 1, 2, and 3, you get 6. That's what makes 6 the first and only single-digit perfect number. Now, that's for the even prime 2. Let's check out the odd prime 3. Now, if you put 3 right here, you would get 2 squared, which is 4. And then 2 cubed is 8, minus 1 is 7. 4 times 7 is 28. Okay. And again, you can verify the sum of the proper divisors of 28 is 28 itself, namely 1 plus 2 plus 4 plus 7 plus 14 sum up to 28, and they happen to be proper divisors of the number. That's what makes the number perfect. Now, we'll do just one more here. P equals 5. And by the way, you can do sigma of this thing right here, and you will get 2 times this number, which is literally the definition of a perfect number. A number k is perfect if sigma of k is equal to 2k. Now, right here, I'm pretty sure you get 496. You guys may want to verify. I'm not going to go through the arithmetic here. Well, let's see. Is it very easy here? If you put a 5 right here, you get 2 to the 4th, which is 16. So this is 16 right here. And then if you put 5 right here, you get 2, 32, 31. 16 times 31 looks like it's equal to 496. Okay? So this is our third perfect number. Notice that you have what appears to be an alternation going on. 6 last digit, 8 last digit, 6 last digit. And I think for 7 you get a number that I'm not going to try to compute that ends in 8. But here, tonight we're trying to prove the last digit of a perfect number is 6 or 8. Now we're going to go ahead and go with this so-called definition of a perfect number, of an even perfect number. And I should say that, folks. It has to be even. They haven't proven there are no odd perfect numbers. So this is the form for all even perfect numbers. And most people think there's no such thing as an odd perfect number, although it hasn't been deductively proven yet. Now, so we're going to use this result here that says any prime number p is congruent to 1 or 3 mod 4. Notice that p can't be congruent to 0 mod 4, because that would be the same thing as saying p is a multiple of 4. We'll say 4k. All right. This is the same right here as saying this would be if p was congruent to 0. Also, if p was congruent to 2, you would have p is equal, and I'm just going to say equals, but notice this is impossible because p would have to be divisible by 2. The only way that could happen would be if p was 2. No other prime could be divisible by 2. So this can't happen. So this is why this little result, this little lemma works, okay? Now, so what I'm going to do is break it into 2 cases. The very first case here, case 1, we'll assume that the prime number has a remainder of 1 upon division by 4. That's what p congruent to 1 mod 4 means. So this is case 1. Case 1, there's only 2 cases we have to examine. Now, a very useful thing happens here with the arithmetic. When you substitute this in, this is what happens. You guys can verify. And we exploit the very fortunate fact that 2 to the 4th ends in 6. Okay, 2 to the 4th is 16. And remember, if you elevate anything that ends in 6 by an integer power, you get a number that ends in 6. All right? And so that's why this piece right here, and I'm just going to write it like this, folks. This number, whatever it is for a positive integer m, has to end in 6. And again, that's because 6 has that so-called, that nice property, okay? This number has to definitely end in 6 because it's 16 raised to the nth power, so it has to end in the digit 6. Now, right over here in a similar fashion, you'll discover this would end in 6, just like over here. Then you multiply it by 2. right? Or you multiply, yeah, you multiply it by 2 and you get what, 12? And you see you would get that this piece right here has to end in 1. And again, you guys verify that on your own. But this part right here would have to end in 6. And then you would multiply by 2 and you get 12 minus 1 ends in 1, right? Okay, ends in 6, then you would have ends in 2, then you subtract 1, ends in 1, right? That's the reasoning. And y'all, in a similar fashion down here, and again, you guys can verify, this part right here would end in 4. Check it out yourself. This part right here would end in 4 using similar reasoning. This guy right here would actually end in 7, all right? And again, this is just the end, obviously. And 4 times 7 is 28, right? 4 times 7, so you get it that the digit would end in 8. So here you get that it ends in 6. Ends in 6. And then down here, this, and again, verify me on this, but I'll double check it. You guys can check it out if you want. But I'm almost certain this is correct here. So 4 times 7 is 28, so this one would also end in 6. End in 8, excuse me. End in 8. Okay. And so that's QED time. Quandam est demonstrandum. Thus we have demonstrated. All right. That is all, folks. Until next time.